Hey, what's up, guys? In the past videos, we talked about stress-strain curve and also the 0.2% of strain. Today, we are going to talk about engineering stress-strain curve as well as true stress-strain curve. So this is what we usually call stress-strain curve. It has plastic region, and after the yield strength point is in the elastic region, and the highest point is called ultimate tensile strength. And after the point, it's the nicking area. So for the stress, instead of keep going up, after the ultimate tensile strength, it dropped. So have you ever questioned why would this drop happen instead of keep going up? Well, this is the topic that we're going to discuss today. So as a hint, the reason of the drop because of the nicking area. Okay, let's get started. So we have engineering stress-strain curve and also true stress-strain curve. So typically on your textbook, what we saw is engineering stress-strain curve, such as the curve like this. But in reality, while you are performing a tensile test, it should be acting as true stress-strain curve as this. So the reason of the difference is because of the cross-sectional area of the workpiece. So in the plastic region, while we keep pulling the specimen apart, the cross-sectional area is actually continually to reduce. So the way we calculate stress is force over area. But the reality is the cross-sectional area is constantly changing because of the cross-sectional area reduction. The way that we plot the engineering stress-strain curve is we always use the original cross-sectional area as the area when we calculate stress. However, after the yield points, especially after the ultimate tensile point, nicking happens. So the cross-sectional area is reducing a lot. But when we calculate, we still use the original cross-sectional area. So actually, after the nicking, the cross-sectional area drops a lot, and it's hard to get instant area. So that's the difference of the true stress-strain curve and the engineering stress-strain curve. So if we always use the instant area, which is always the true area, then the stress-strain curve will be acting like a true stress-strain curve. And in the true stress-strain testing, we could use an equation to estimate the stress-strain curve, which the true stress is equal to strength coefficient times strain power to strain-hardening exponent. We can use this formula to estimate the shape of the stress-strain curve, especially for the plastic region. And the K is strength coefficient, and N is strain-hardening exponent. So for strain-hardening exponent, that term defines the material's tendency to be work-hardened while plastically deformed. And the value of strain-hardening exponent is between 0 to 1. And 0 means the material is a perfectly plastic solid. And if the number is close to 1, means the material is 100% elastic solid. So if you wish your metal can be work hardened, then you probably want to choose the material that their strain hardening exponent is close to 0. So actually for most metals, their N value is between 0.1 to 0.5. And here are some strength coefficient and strain hardening exponent for some common materials, such as low carbon steel, 4340 steel, and 304 stainless steel. It listed the strain hardening exponent. As you can see, they're most likely less than 0.5, means they can be work hardened. And also their strength coefficient, and the units is megapascal. So the stress-strain curve that we saw, they're most likely for ductile metal. It doesn't mean that all materials will have the same or similar stress-strain curve. So the curve that we saw, they are for ductile material with a significant work hardening. So note that work hardening is happening in the plastic area. And if the plastic area is pretty flat, so it means the material has a low work hardening rate. And for brittle material, it doesn't have a plastic area, so only in the elastic area. After the yield point, the part will break, such as glasses, ceramics, and also some plastics in the cast iron. And also for plastics, especially ductile plastics, it has structure breakdown and reorganization area after passing the yield strength point. And also the yield points could be discontinuous. So materials like this has discontinuous yielding area. And for composites, fibers, the stress-strain curve could be acting like this. So this is about true stress-strain curve and engineering stress-strain curve. Thanks for watching. We'll see you next time. Bye.